5 is all about radical chemistry. They're going to go into a whole bunch of extra stuff when it comes to radicals because there is a lot of kind of interesting chemistry that is associated with it. I'm going to try to cut over the top of it to just cover the main bullet points from it because for the most part it's not shown or worked with all that often. You notice that I've listed 2 different functional groups on this slide. What are those 2 functional groups? So one you should be able to pick up right away, the alkene. The other one's a little bit trickier because we typically don't classify it as a functional group. It's an alkane. Remember when we talked about alkanes briefly at the beginning of the semester, there's virtually no chemistry with them. Why? They're really stable. Why? No charge. Why no charge?
They're very close in electrons.
All the atoms within your alkanes are carbon to hydrogen, or carbon to carbon bonds, or carbon to hydrogen bonds, single bonds. Those sigma bonds are incredibly stable, particularly because there's very little difference in electronegativity between your carbon and your hydrogen and carbon. That then makes your alkanes incredibly stable and incredibly unreactive. Okay? Your alkenes are a step up in reactivity because of that pi bond with those pi electrons. But likewise, we also have some slight variances off their reactivity. Okay? So what we're really concerned about is trying to get our alkanes to react. That's our primary goal. To do that, that's where we have to bring in radicals. So the radicals change the dynamic of everything we've talked about this semester. So we've got an example of 4 radicals. What do all those radicals have in common? They have a single unpaired electron. That didn't really help. Okay. So that unpaired electron is ultimately what's driving the chemistry of your radical reactions. Okay. And we'll notice that there's several different sources for these. Okay. Typically, we see that first one as an initiator. Right. It's never shown as the radical form. We'll talk about where it comes from. Oxygen is a nice reactive species. Oxygen gas is technically a diradical, which is one of the reasons why it is a particularly reactive molecule and we use it for breathing, is that diradical species can allow us to do some cool chemistry. We can make a bromine radical as well, which is the most common one that you'll go through and see as far as reagents, is having a bromine radical. And then as your intermediate, you will typically see a carbon radical. Okay, as far as its reactivity goes, your radicals are unpaired electrons. Right? So if we're going to compare its reactivity of a radical, say, to something we've already looked at, cations and anions, it turns out the radicals best match the cation characteristic. So if we have a radical, our radical structure tends to be sp2 hybridized. The radical itself, that unpaired electron, is sitting in an unhybridized p orbital. Okay? So when we're going through and doing these reactions, we're really concerned about making stable radical intermediates, which ultimately means stable carbocations. This goes back to our unimolecular type reactions. One of the next biggest issues we're going to have to worry about is that they will react with the most available electrons. That available part becomes exceedingly tricky, or something that we manipulate a lot when we move into the lab, not so helpful when we're looking at mechanisms. What we end up changing is concentrations. The concentration is very rarely actually specified within a mechanism or within a reaction problem, but by changing the concentration, you can get vastly different results out of your radical reactions. Okay, so kind of neat stuff. So one of the very first things we need to do is go through and make our radical. Okay. Because we're doing a slightly different process than we've seen before, we are also going to now reference the mechanism slightly differently. So there ends up being 3 primary stages within a radical reaction. The very first stage is the initiation. Okay, it's this try that again. It is the formation of a radical. So if we take a look at the 2 reactions shown, We do not start with a radical, but when we run the reaction, we end with a radical. Right? Radicals are very, very reactive, which means it's very difficult to actually get them in a natural state or identify. So we'll almost never see them as free radicals roaming around. They get transferred or get formed in situ. So one of your first options is we're going to start with this compound, and we want to break that apart to form two of our radical species. How can we add arrows to represent that bond breaking, to generate equal radicals? What we're going to end up using is now referencing a single electron motion, not two electrons at any given instant, but only one. So if we had done this as a normal method, we might have said, oh, two electrons transfer over. But then do I end up with two of the exact same species? No, one becomes negative, the other one becomes positive. Okay, so instead, what ends up happening, that's a big eraser, is I use a half-headed arrow to say one of the electrons in that bond goes to that oxygen. But what happened to the other electron in that bond? It had to go to the other oxygen. This is one of the things that can be obnoxious about our radical reactions. Okay? Typically, when we dealt with normal reactions, we only needed one arrow, and it represented the motion of breaking a bond. When we deal with radical reactions, you need two arrows. Okay? You have to specify both. The electron isn't assumed to just move back to an original atom. This is also a different type of bond cleavage, because we're not pushing the electrons solely to one atom. Okay, so what we reference this as is homolytic bond cleavage. The electrons go back to their original atoms. This same process can happen with bromine, okay, elemental bromine. We can split that open in this homolytic cleavage. Once we've got the radical, we can potentially go further on and have that radical do all sorts of weird, crazy stuff. Okay, and that's what that bottom part is signifying. Oh, there it is, just triggered. To get this to initiate, these molecules, while reactive, are somewhat stable on their own, okay, and so they will stay on their own. For instance, when we looked at bromine, bromine doesn't immediately jump into becoming a radical. We have to cause it to become a radical. Okay? That first species is a peroxy acid. Our peroxy acids, okay, don't just jump into being radicals. We have to cause them to become a radical. That causing process is relatively easy to do. Okay? In one case, with our peroxy acid, all we got to do is add a little bit of heat. Okay? You add enough heat, that weakens that bond enough that it breaks apart, and you've got your free radical. Okay? The other option that you'll see with these is light. How many times have we seen light as a reagent in our chemistry? Okay, you potentially see it in biology. Right? How about in organic chemistry? Where else have we seen light so far this semester? Fair enough. Spectroscopy uses light. Does it do any chemistry? No.
But then you have the optical activity.
Optical activity still is not doing any chemistry. It's only detecting stuff. Have we used light to do any chemistry this semester? No. Guess what's a really big tip that you're dealing with radical reactions? Light. Okay? It can get written out as just light, or you may see it more commonly written as H nu, which happens to represent the energy of light. Okay? It's frequency times Planck's constant. Okay? So it's representing light, and we're just saying it's some energy of light that's being involved in this. Okay? Once our radical has formed, it can then go on to do all sorts of other crazy chemistry, and that's going to depend on what kind of conditions we put our radicals under. So, the first one we'll address is our sigma bond reactions, which typically happens with our alkanes. Okay? What we're looking at now is a propagation. So our big difference here from our initiation is that we're starting with a radical. Okay, we've got a bromine radical, and we end with a radical. Okay, so that's now a propagation step. Okay, so we've got a variety of propagation steps shown here. It doesn't have to be the exact same thing. As long as you start with a radical and end with a radical, it's propagation. Okay? So now the next part is, what does this do for us? Okay, well, I gave you just a simple alkane. What alkane did I give you? Propane. 3 carbons, we've got a propane alkane. Yes, I'm drawing those hydrogens on in a bad fashion for those of you doing the homework and have been exceedingly frustrated by drawing this answer and getting it marked wrong. Yes, I've drawn those on incorrectly. You can't just imply some hydrogens and not others. Okay, so in this case, we're only trying to highlight the fact that we have different potential reactivities. So what's happening in this first step? The bromine reacts with something. What does the bromine react with, or the bromine radical? How do you know it reacts with the hydrogen? Look at the product. Product shows HBr is formed. Why would it react with the hydrogen? No, that hydrogen technically actually owns no electrons. Its electrons are involved in the bonds. If it was positive, we're assuming heterolytic bond cleavage, which is the same thing that we talked about previously or previous reactions. This is homolytic bond cleavage. So it's not positive. Why does the bromine react, or the bromine radical react with hydrogen? Nope, no charge. So it's a completely different system than we've seen before. There is no charge in this. We cannot have charge. Why does the bromine react with hydrogen?
Is it because the bond is not as strong as the CC bond, or is the CH bond is weaker than a CC bond?
We could look at bond strength, that our CC bond is stronger than our CH. That's an interesting idea. Say there's another one. Where are the hydrogens? On the outside of the structure. Where are the carbons? Inside the structure. Which is going to be easier for the bromine to react with? The outside, because it is more accessible. Our bromine radical is going to react with the quickest and easiest and most available thing possible, which in this case is going to be hydrogen on the outside of the structure. That's why it goes after the hydrogen. It's a concentration thing. All right? So, how does it do it?
Why does it want to react with anything?
So it is charge neutral, but we have an unpaired electron, and that's what makes it reactive. Okay? The sheer existence of us having an unpaired electron makes that reactive. So, how do we show it? So the bromine radical donates that one unpaired electron to either one of the hydrogens, because I'm showing 2 products here, right? So let's go through and show how that potentially worked. Which hydrogen do you want to go after first? Closest one? Okay. How do we draw that arrow? Where does our electron start? At this point. Our radical bromide? Okay. There's our arrow starting. Where does it go? Goes to the hydrogen. That looks a little weird. What's problematic about that? Can we take electrons from an atom and give them to another atom? No, we only go atom to bond. This is a little weird. Okay. Let's just work with it and see what happens now. Hydrogen would now have how many electrons around it? 3, which is exceeding its octet. So what do we have to do? We have to break a bond. What bond do we break? The carbon-hydrogen. So let's take those electrons and move them where? Okay, so I heard 1 to the hydrogen. That seems reasonable. Hydrogen's part of that bond. That works. Where should the other electron go? To our carbon. This gives us our carbon radical, shown in purple. Where's the bond now between the H and the Br? By the way, if you're drawing this, particularly in pen, you might want to stop. This doesn't quite make sense. This goes against how we move electrons. We move electrons to bonds. We don't move electrons from an atom to another atom. It doesn't work that way. Okay? So what we end up having to do is modify our rules to better accommodate the reaction. Okay? So for sure, I completely agree with our electron going from the bond to that carbon, single electron. We now have our carbon radical. But what do we do with the other electron on the hydrogen? It needs to somehow be going to the bromine. But that's now just the reverse of what we already drew, and that's going to still be problematic. Okay? We can't take electrons from an atom and give them to another atom, but we can take them and give them to a bond. So I'm going to take that single electron and I'm going to go out into this new space. In that new space, the bromine radical is going to meet up with the hydrogen and share its electron. I now have two electrons in between hydrogen and bromine. What do I now have? Now I have a bond between the hydrogen and the bromine. Very, very odd. Okay? This is also something that if you go through and take a look at the homework, you will notice you do not see any questions like this. It's very hard to have electrons go to the middle of nowhere and assume that you're doing something correct. Okay? So I've removed those questions from the homework because I don't think it's super relevant to this. What happens in the case of our red product? Same thing, sort of. What do you mean by same thing?
I mean, like, the movement of the electrons is same, just for the hydrogen.
Just pulling off our other hydrogen. So we end up with two possible products, which I've colored here now as red and purple to help us see that difference. That's our two possible products that come out of this because we had two possible types of hydrogen that could be removed. The question becomes, which hydrogen is the preferred hydrogen to be removed? Oh, you're actually answering. Okay. Which one? Why the red one?
Because of the carbocations, same thing, you would stabilize better that way, lower energy than it would at the end.
Radicals are equivalent to carbocations as far as reactivity. So if we're given these two possible options, we prefer the red product over the purple because that red product gives us a more stable radical. That is now going to be our favored intermediate. Can the other one still happen? Yes. Depending on conditions, it may form in very small amounts or larger amounts, and we'll look at those conditions a little bit later. We now have a carbon radical. That carbon radical is inherently unstable. What's the next thing it is most likely to encounter? As a hint, it's already drawn up there. The odds of it encountering another bromine radical, that is an interesting question. That would be nice because then we're done with radicals. But remember, radicals are inherently unstable. They have very short lifetimes. The odds that we get two radicals encountering each other, not very likely. Okay? So we would not predict two radicals impacting each other, and that is not our next step. Okay? What we do end up showing now is our carbon radical reacting with bromine. Why elemental bromine? It's in there in a much higher concentration than any of our bromine radicals or any of our other side products, say like HBr. Okay. Could it have just as easily reacted with another alkane? Yeah, that's perfectly fair. What would happen in that case? You form the exact same radical and you neutralize a radical. Nothing really changed. So only when it encounters a new molecule, bromine, do we actually see the potential for a product coming out of this. Right? How does that mechanistically occur? We're taking our single electron, we are moving it to the space where a new bond will be forming, and we'll take a single electron. Oh gosh, that was an ugly arrow. Let me try that again. And we'll move that single electron to the space where a new bond is forming. I now have to account for both electrons in that old bond. I add one more arrow, taking the electron back to its parent bromine. The result is I've now done a substitution. Whoops. Oh well, I said it already. We've done a substitution reaction. What did we substitute? We just substituted bromine for hydrogen. Why is that a little bizarre? Every other substitution reaction we've done, the atom that we substituted on our substrate was electronegative. Actually, it's a really good leaving group. Is the hydrogen acting as a leaving group in this substitution? No. Okay. What makes this even more important is that we've now gone through and taken a structure, say an alkane, which had no reactivity because there's no polarity within those bonds, and we've now turned it into what was that, Michael? We have an alkyl halide. What's special now about our alkyl halide? It can now do substitution, elimination, and open up all of our other chemistries. Right? So our free radical reaction takes us from neutral structures that are useless, converts them now into something that's useful that we can potentially do more chemistry with. That is pretty much the only reason we use our radicals. Okay? Between these two possible products, which is our favored product? So our red product or our purple product? Why do we favor the red product? Its intermediate is more stable, which means it can form faster. If it forms faster, it can then get to the product faster. Okay, so it's all about the stability of that intermediate. If your intermediate is stable, you're going to get to a final product quicker with a larger concentration. Okay? This is your propagation step. Just to reiterate, we started with a radical and we end with a radical. That is your propagation. At some point during our reaction, we have another possible thing occurring. We could take our two radicals, or any two radicals, and combine them with each other. What is the result if we combine two radicals with each other? We are now forming a new bond in between, and we generate our alkyl halide, and you'll notice there is no radical. We started with something reactive as our radical form, and it is now neutralized into our alkyl halide. We have no more radical chemistry. So when we're looking at our third and final phase within our radical reactions, we have the termination. You start with a radical and you end with no radical. Okay? There's a variety of ways that you can go through and do a termination. You've got three nice examples given to you nice and easily up at the top. Okay? Those are probably more than likely what's happening in solution. You'll notice that one odd one, this is one of the reasons why I don't like radicals. There is a likelihood that I'm taking two of my carbon radicals and reacting them with each other to generate a new product. What's odd about that new product? It's not an alkyl halide. Okay. Our radicals are a mess. They can do pretty much anything they want, okay, to stabilize those radicals. How can I prevent, say, that side product from occurring? What's that? Not quite. It's all about the likelihood of encountering that next reactive molecule. If I've got a ton of bromine in that reaction, the odds that my alkyl radical encounters bromine is very, very high. The odds that my alkyl radical finds another alkyl radical, not so high. Okay? So it is purely a probability game. If I want this dialkyl compound at the end here, how could I make sure that I get a lot of that as a possible product? Increase the concentration of my alkyl compound, decrease the concentration of my bromine. Okay? Because the bromine's the one that's generating the radical. The last thing that we could potentially do to kill or quench your radical reaction is to go through and add some kind of radical scavenger. Okay, so all this is we're adding another molecule that is in a radical state that can very quickly react with any other radicals in the solution to form a new bond that can be then filtered out of the solution or isolated some other way. Okay? Your body is pretty phenomenal at this. Your body has tons of radical scavengers. Why? Because free radicals are bad for your body. Technically, they're very important, actually. We need them to do a lot of different reactions. However, we want them to only happen in one location. And if that location happens to now be your entire body, that gets a bit problematic. Okay? So biologically, we've invented scavenger molecules to go out and grab free radicals. Okay? One of the things that you will find super common within those scavengers is tons of pi bonds. Okay? Those pi bonds react very well with radicals and kind of neutralize the chemistry through resonance. Okay? Conjugated pi systems are phenomenal at reacting with radicals and stabilizing them. Okay? So, utility. What can we potentially do with this? Well, if I now take a look at this reaction, I'm starting with a methyl cyclohexane. I want to get to a methyl cyclohexene. Okay? To get an alkene as a final product, what kind of reaction do I need to do? I need to do an elimination. So we can go back and take a look at what I start with. To do an elimination, what do I need? A base is a good possible option, which is really going to start pushing an E2 mechanism. What else do I need to do an elimination reaction? We need a leaving group. We go back and look at our starting material. Do we have a leaving group? No. So starting with the methyl cyclohexane, we got nothing. We cannot do an elimination reaction. So what we have to do is somehow change the methyl cyclohexane structure with some other chemistry so that I now have the conditions met to do my elimination reaction. What do I do? I will run a radical reaction by reacting it with Br2 and light or heat. It's typically light when it comes to bromine. That then gives me as a product what structure? Bromine needs to be attached. Where does the bromine need to be attached? At the methyl group. Why at that methyl position? That will generate our most stable radical, which then means our bromine will react at that location. I now have a good leaving group. I can now move on to my elimination reaction, add a strong base, run my E2 elimination. Kind of make sense? So for all synthesis questions, both for the rest of the semester, which isn't much, for the final exam, and anything you see in second semester, when you see an alkane, the very first thing you should do, radical reaction, every single time. Do the radical reaction, get that alkyl halide on there, now you can do some chemistry. Right, so that is our big use out of our radical reactions. Questions on that? Okay. So, some reagents that can pop up here. We've got all sorts of halogens that work well for doing your alkyl halide substitutions. Bromine is a phenomenal one. Okay? Typically light, and it is very selective, meaning when we go through and do the bromination reaction under radical conditions, we put a bromine at very high yields at that tertiary position. Okay. If we move to chlorine, you'll notice I haven't talked about chlorine yet. Okay. There's a slight problem with chlorine. What is that problem? Not selective. What does that mean? What's that?
Just react with a lot of things.
Be more specific, it reacts with a lot of things. If we take a look at our starting alkane, where would we put the chlorine?
Anywhere.
Pretty much anywhere. Probably the most likely spot is going to be at any one of these carbons. Why would those carbons be the most likely to put a chlorine?
Outside,
What's that?
if they're on the outside, easily accessible.
This CH3 is accessible. And our tertiary carbon would generate the most stable radical. It's still giving you that radical intermediate. Why do we see it happening on those other carbons, not at the most stable and not at the primary? Nothing to do with steric hindrance. The methyl would be even more accessible. Our radical reactions are driven by concentration. Why is that important now?
There's more of those than there are.
If we look at all of those other positions, they are all secondary carbons, all of them with 2 hydrogens apiece. There are 2, 4, 6, 8, 10 possible hydrogens versus 1 for the most stable versus 3 for our least stable. 10 possible positions, our chlorine's going to go there because that's where our highest concentration of reactive hydrogens is located. Okay? That's our issue with our chlorination reactions. They are horribly unselective, which means we can kind of ignore them. Fluorine is also a radical. You'll never see fluorine used under radical conditions. Okay? It is horribly not selective. Okay? It is exceedingly reactive. The fluorine radical is now massively, massively reactive. Why would the fluorine radical be so much more reactive than, say, the chlorine or the bromine? Electronegativity and smaller, which is dealing with we're looking at forming a radical, which is roughly equivalent to a carbocation. If we're looking at fluorine being the most electronegative atom, is it ever going to want an unpaired electron? Okay. It's now exceedingly reactive. It wants to grab electrons immediately. So anything that is remotely nearby, it will grab. Okay. It is now small, so it cannot stabilize that positive charge. Okay. So both the size and the electronegativity contribute to fluorine being an exceedingly non-selective reagent. If we went through and tested it, it would probably blow up this room. Okay? That is how exceedingly reactive it is. Okay? So if you wanted to put a fluorine on a structure, you don't do it through a radical mechanism, okay? Because that is exceedingly dangerous. The last possible option, iodine, is another halogen. We could go through and use iodine. It is even more selective than the bromine. The problem is it is so selective that it takes forever to go through and run. Okay. The radical of iodine, once it is formed, is now really, really stable, lower electronegativity, massive size. Okay. It is not going to be favorable to go through and do a substitution with our iodine, which means really when we're looking at the reactivity for our radicals, the only one we need to worry about is the bromination one. Chlorine can pop up if they just want to be obnoxious with a test question, but for the most part, bromine is all we're going to use synthetically. Questions? Okay. We could go through and look at an energy diagram for this. So if we look at our chlorination versus bromination reactions, okay, what do you notice as a significant difference between these two energy diagrams?
Difference in the energy of the product and also the difference in the activation energies.
What do you mean the difference in energy of the products? What is the energy of any one of those products?
It's higher than the sodium.
So it's not just the energy of the product, it's relative to your starting position. What type of reaction was run for the bromination? It's an endothermic reaction. What happens for our chlorination reactions? Exothermic. This is actually why we have a strong favoring or selectivity of our bromination reactions versus our chlorinations. Our chlorinations are exothermic, meaning what we're going to try and do is react as quickly as possible. There's this process this term known as the Hammond postulate. If we're looking at the activation energy for any individual step, the activation energy is always closest to the reactant or product that is closer to it in energy. I know that sounds kind of weird. Take a look at our reactant for the bromination reaction. There's our big X. Take a look at our product for the bromination reaction. Call that Y. The transition state has to be somewhere in between. Where should that transition state be closer to? The reactant or the product? The product. So if there is now a significant difference in energy of those products, what is that going to now make a very large change to? The transition state energy. If your transition state energy changes significantly, what happens to the rate of the reaction? Going to change very significantly. What happens when we look at the exothermic reaction? X to Y. Where's our transition state closer to? Reactant. Is there a difference in energy of our reactants for the chlorination reaction? No, they're starting with the exact same reactant, which means what's the difference in our transition state? Virtually nothing, which means there is now no selectivity towards getting towards that product. Right? We have the exact same activation barrier to go through to our final product. We really only see that big difference when we're looking at an endothermic reaction. If I try to draw an iodination, I think I got that right. An iodination reaction, where would I put the intermediate? It's going to be very, very high. Why is it very, very high? It's very, very selective. The iodine radical is inherently exceptionally stable. The carbon radical, not so much. We're now going in an extremely endothermic reaction. It doesn't mean we can't do it, it just means that's not going to be a very likely reaction to occur. So one of the reasons why we don't do iodination reactions. Right? So the end result out of this is that if you have a choice for your synthesis, choose brominations. The brominations work better. Okay? What about stereochemistry? Ow! Let's go the other way. What would we expect for our product here? What would we draw? Let's first focus on the substitution, right? Where should the bromine go? 1, 2, 3, or 4?
2 or 3.
Why 2 or 3?
Because they would be the same.
They're the same. Cool. So let's go ahead and just draw on our product. There's our bromine at position 2. Once we've done our reaction, we need to now evaluate, do I have to worry about anything further? Well, what is an issue with this product? That is a stereocenter, which means to fully evaluate the reaction, I need to evaluate stereochemistry. Where should that bromine be?
Number 1. Like the most preferred spot.
Wedged or dashed? Why both? What's your intermediate? What did we say the hybridization was of our intermediate? sp2, which means that radical can react either above or below the plane with that p orbital, which means we get 2 products. We get the bromine wedged and we get the bromine dashed. Okay? So we end up again with two possible products as we go through and do our reactions. Okay? So you got to watch out for that. Questions? Okay. One way you can think about this in general for all reactions is if we start with an optically inactive material, we need to end with an optically inactive material. Okay? And that can mean we either have an achiral compound or we have a racemic mixture of products. Our alkenes are all optically inactive, so when we go through and do our alkene additions, we ended with enantiomers most typically coming out of them. Okay? Unless, of course, our starting compound was optically active, in which case we got an optically active product. Our alkane being optically inactive means we're going to get an optically inactive mixture of products. So the next question, what happens now? New problem. What would you predict to be the product? Anybody know how many quizzes we've had? Let's see. I don't think I got enough. It's close. What do you mean 4 products?
Well, probably go ahead and separate one electron to each carbon to each side, and then the bromine will then attack each one from the top end.
So what you're referencing is that we're breaking the pi bond as a radical, right? That's what I'm hearing. Bromine is what cleaves as your radical. That's your focus. Okay. The question then becomes is where does that bromine radical then react? While the pi bond is a possibility, what we want to go through and do is evaluate those possible products. So if you're saying it's going to form your radical first, what you'd be making the statement of is that this is what we'd end up with as one possible product. The bromine radical comes in, picks up a single electron from the pi bond, and forms a radical at the other position. Yes or no? You agree with that?
It would come in also on the other side too.
So we also have the potential for the other direction. So yes, we have the possibility, and I'm just going to say plus minus in this case, for all sorts of stereochemistry coming out of this. Yeah. Okay. What kind of carbocation do we have formed? Secondary. That's allowed. I mean, it's equivalent to a carbocation. Not too bad.
I guess my
Sorry.
question was, wouldn't it be the case that the more likely reaction would interfere with the second carbon on the chain there because it'd be a allylic secondary?
What happens if we pull a hydrogen off and we form this as our product? I now still have a secondary carbocation, or sorry, secondary radical, but it's a little bit different. It's not just a secondary radical, it is secondary allylic. Which is more stable? Secondary allylic, which means which of these two intermediates is the more likely one to form? The second one, and we end up not seeing the first one happening. Okay. So if we up the reactivity of our starting material by bringing in an alkene, that changes the chemistry around a little bit, and what we end up seeing is this allylic substitution. And we put our bromine there, or on the other side, I did intentionally draw it so it was symmetric. This would again be plus its enantiomer, so we have the plus minus. We'd have two products. Okay, well, as you mentioned already, because we end up with that intermediate.
Would it ever attack the 1 or 6 carbon just because that actually is more available? You know?
So this comes down to the selectivity of bromine versus the other reactions. Bromine will always form the more stable intermediate. Okay? So we will not see pulling hydrogens off the tail end because those end up forming radical or primary radicals, which are just not stable. Okay? So that doesn't happen, at least not to a high amount. Does anybody else see a potential problem with this? Yeah.
So, one is a carbocation. I can't understand why it is stable because of the ion, the electrons will moving like between. But when it is an electron, like when it's a radical.
What is the resonance structure for this? It's a good question.
The radical over something like that's more stable.
There's your radical. So you're right. You do weird resonance with this. You have to do these half-headed arrows all the way through. Okay? That is absolutely still valid. Right? And that could potentially lead to another product out of this. Okay? But the resonance stabilization is still the same. You're just doing resonance with homolytic bond cleavage as opposed to heterolytic. So watch really carefully. We're going to make one swift change. What product do you expect?
It's just an addition reaction.
What type of reaction occurred? An addition. Alkene, bromine, that's a standard addition reaction. If we wanted to get even more fancy on it, we could show that these were what arrangement? If that one's wedged, what's the other one? Dashed because it's the backside attack. We're looking at an anti-addition because we form the bromonium intermediate. Okay. So, interesting dilemma pops up. If I've got a lot of bromine, I have to form the radical. If I've got the radical, I can do the radical substitution. What happens if the radical doesn't form, or it doesn't form in high concentrations? The bromine starts reacting in a standard addition mechanism and gets us to our addition product, not our substitution. This is an interesting dilemma. If I want the substitution, I want to limit the presence of the bromine so that I don't get the bromine addition. Because we saw in lab, the bromine addition is incredibly fast. Okay, we used it as an unsaturation test, a classification test for the presence of an alkene. You just swirled it around, the color disappeared instantly. Okay. So if we're trying to do the radical substitution, we have to have something compete against that addition, which means the concentration of bromine needs to be very, very low. But if it's very, very low, what's the odds I'm going to get any of the substitution? Also very, very low. So we want to come up with some way that we can generate the bromine in situ that allows us to do the radical substitution. The reagent that allows us to do this is known as NBS, okay? N-bromosuccinimide. Okay. What this reagent does is it decomposes to form bromine in very, very small concentrations. So small that if you expose your reaction then to light, the light can then cause that to form your radical. We can now do the radical substitution instead. Right? NBS also has an added feature. Right? Bromine is exceptionally toxic. To run a reaction with a whole bunch of bromine, we're potentially risking our lives. So we want to limit the concentration of bromine further so we don't risk our lives. How do we do that? NBS does a good job of that. Okay? The side product that comes out of that, we can then try and clean up and throw away, turn into the waste, all that fun stuff. Those of you interested in green chemistry may look at this and say that's not a good idea. Okay? Green chemistry is all about minimizing the amount of side products and impurities in a possible reaction. If we just ran a standard substitution here, we sacrifice one atom. We lose one HBr from our structure. If we use NBS, what does this species do? We throw it away. We're not losing just two atoms. We're losing two atoms and a giant structure. Okay? So as far as green chemistry goes, NBS is a pretty horrible option as far as atom efficiency. Okay? As far as safety, that's a little bit better. So depending on how you want to classify your chemical reaction, you may say this is actually a good one versus a bad one. So radical substitution reagents, bromine and light. We're looking at doing our reactions with alkanes. Chlorine and light, you might see, not a very good option. Last one, NBS and light or heat. Both work with the NBS. The bromine will substitute a hydrogen at an allylic position. Right? It'll still work with the alkanes, so we could use it for all of those. So very commonly, particularly at ASU, I know one instructor, when doing any kind of radical reaction, all of his keys say NBS for any type of radical reaction, because NBS is a nice go-to, relatively mild and safe. Okay. Questions on that? Okay, so what we have now covered are our radical substitutions. Turns out we have other types of substitution or other types of reactions happening as well. Remember that whole peroxy acid thing? Okay. You'll notice that we haven't shown that yet. Okay. Well, our peroxy compound will decompose into our radical, and we can use that to do yet another type of reaction. Okay. So we now take that peroxy compound, we'll mix it with an alkene, and we'll mix it now with HBr. This is an interesting addition. Okay, we're not using Br2 now, we're actually using HBr. Why is the addition of HBr a bit odd? It's a strong acid, which means what kind of bond cleavage do we expect out of HBr? Heterolytic. If we ran this reaction without that radical initiator, so let's erase that temporarily, what would we expect for our product? The hydrogen and the bromine add to the structure. It's not an anti or syn addition because we form a carbocation intermediate. Where does the bromine go? The secondary position, we form the most stable carbocation with the initial reaction of our hydrogen. When we now go through and add that radical initiator, guess what the product is? Whoops. Oh, no, that'll work. We get the bromine going to the primary position, which seems very, very counterintuitive. That would suggest we're forming some kind of unstable carbocation. It's a little bit weird. Right? Well, it helps to go through and look at your mechanism. The most likely thing for our radical to find or encounter will be HBr. When we run this reaction, we have a very high concentration of HBr, which means the most likely thing the radical will encounter will be hydrogen or bromine. Which would it react with preferentially? Why the hydrogen? Okay. Look at your possible products. If it reacts with the hydrogen, we end up forming acetic acid. Yes, it's an acid, but it's actually a weaker acid than HBr, so that's not too bad. What if it had reacted with the bromine? And then we'd have our bromine radical. What if it had instead reacted with the bromine? You're getting two very electronegative atoms attached to each other. That's not particularly stable. That's going to end up undoing all of that radical formation that we'd already done, and we end up forming a hydride radical, or a hydrogen radical, also not particularly stable. So our radical reaction will preferentially pull off the hydrogen, and we end up forming bromine radical that can now potentially react with our alkene. So now the question is, how does it react with the alkene? An electron from the pi bond, for lack of a better way to locate it, comes out and will react with the bromine. What happens to the other electron in the pi bond? Moves to the carbon. Moves to which carbon of the pi bond? Why does it move to the secondary one? we would expect it to move to the secondary position. So we have two possible options. We have a secondary radical or a primary radical. The secondary is more stable, so the primary reverses and does not actually end up forming. Now, what does our compound most likely encounter?
Another HBr.
Probably encounters HBr. Very unlikely for it to encounter another bromine radical. Okay. Also, very unlikely for it to pick up bromine from our HBr. That's not a particularly likely situation because we end up forming a hydrogen radical. So what reacts instead is our hydrogen reacts with our radical. We end up reforming our bromine radical, and we now have our final substitution product with the bromine at our least substituted position. If we wanted to invoke the names of old dead guys, this would be anti-Markovnikov. Markovnikov said hydrogen goes to the position with more hydrogens. This is anti-Markovnikov because where did the hydrogen go? The position with the fewest hydrogens. This is why his rule is pretty meaningless. If you track the chemistry, that tells you where the atoms go. There's none of this memorization of, oh, it's anti or not. That means you have to know the chemistry. That is an extra added step to this that makes it more difficult. Questions? Okay. So we have two ways to react around an alkene. What products would we expect out of these? I'll give you some time to think about it, come up with some answers. I'll take that as a... NBS is our standard for radical substitution as a reagent. Okay? We're putting in a very small concentration of the bromine. That's then going to favor a substitution at the allylic position. We've got a whole bunch of variety of different places that we can go through and do this one. Could have put a bromine up there. We could also put a bromine out at this other position. Okay? So pick one or the other. Okay? There are potential rearrangements that could come out of this because our intermediate ends up being an allylic radical potentially occurring at any one of those positions. And it would be a primary allylic radical. So our rearrangement is really just resonance, putting the radical maybe at the tertiary position. Why does that potentially cause issues? Let's go ahead and just say that we put the bromine up here for the moment. Our other product could potentially be putting the bromine there. Between those two, which one's our favored product? Depends if you're looking at kinetic versus thermodynamic reactivity. Your thermodynamic product is the first one because why is it more stable? It's the more substituted pi bond. Okay. The more substituted pi bond is then going to be your thermodynamic product. In the other reaction, we add hydrogen and bromine, but we add them the opposite way of that we would normally predict, because bromines just do the opposite of whatever we want them to, and we put our bromine at our least substituted position. Okay? Questions? How do we know we ran these as radical reactions? What's that? No, looking at the actual reactions. How do you know that you should be doing these as a radical, not as, say, a standard addition? Seeing light, as soon as you see light, Radical. Do it. Okay. The other one does not have light, though. How do we know that other one is a radical reaction? But heat shows up under elimination reactions. So heat isn't necessarily going to say, oh, it's a radical reaction. What you're looking for is the radical initiator, the ROOR. You have an oxygen-oxygen bond. Okay? That's your radical initiator. So those are the things that you need to kind of trigger on. Okay? Questions? Okay. One of the last things that popped up in your homework was something known as the Birch reduction. There's only one question on it, I hope. It is using sodium metal, because sodium metal can act as a reducing agent. So if you watch that alkene, the rest of the alkene chapter, sodium metal can be used to reduce alkynes. Take a look at the final product out of this whole mess of a mechanism. What happened when we reduced the alkyne? One, two, three, triple bond, and we end with 1, 2, an alkene. Most of our reduction reactions are hard to stop. So if we just add H2 and platinum or palladium, they will go all the way down to the alkane. Okay? We can't stop them at the alkene. Okay? There is one way to stop it, that is to poison your catalyst. Okay? Or you can follow a different mechanism using a different reagent. Sodium metal and ammonia does that. Okay? Not only does it stop it at the alkene, but it adds an extra little added bonus to this. What is the arrangement of the R groups? Trans. When we use our standard reductions with our standard metals, the arrangement of the R groups is always cis, because they're running syn additions. That forces that arrangement of your R groups. Sodium metal allows for the trans product. Turns out sodium metal is reactive enough that you can go through and use it on aromatic structures. You get a mess of a mechanism coming out of this. The primary thing that you need to be focused on is your first intermediate. What's the most reactive thing in that intermediate?
The charge.
The negative charge. So what happens if I go through and say change the structure? What do I expect for a product? That negative charge is reactive. What do I want near it? More electrons, less electrons? Less electrons. So if I use a standard R group, an R group means typically something like carbon, which has electrons. Do I want the negative charge forming on the carbon of that R group? No. What do I end up with as a product? Your negative charge comes out at the other position. What happens if we shift to the other material? What charge is that atom? Positive. What charge do we want to be close to that positive? The negative. What happens as a result? It specifies the relative arrangement of where the double bond ends up shifting, depending on that group, because you're putting charge next to the negative charge or not. I know we're done. There's the reaction summary for everything within radicals. Everything's up there and ready to run with. Okay?